Wilson here, and we're going to start day 5 by looking at similar shapes. So this topic is pretty simple. It can get a bit harder, which we'll do in the next video, but this should make perfect sense. So what we have is we have two triangles and we're told they are mathematically similar, and when we know that, it means one is a bigger version or a smaller version than the other. And because they're an enlargement, it means the lengths are following a certain scale factor. Now, you will always be given some information that matches the same size on both shapes. So, for example, I've got this here, and I'm told on the bigger shape how long this one is. So, using these two, I can work out the scale factor. If you didn't quite get that, I'll explain it this way. So, I know this one's 10, but I don't know what this is, so I can't work out the scale factor yet, and the same is happening here. So, there should be two sides with information on that you can use. Now, an easy way of doing it is the big one divided by the small one. That will always give you the scale factor. I personally just like to look at it and say, right, is this double? No. So I know it's less than double, and in fact I can see that if I add on half of this, I get that, which means the scale factor is 1.5 times bigger. 1.5 is adding on an extra half. So using that knowledge, if this is 10, I've got to times this by 1.5 to get to x. So half of this is 5. If I add that on, this one must be 15. Now it's a bit harder because we've got the bigger version. So in this case we have to divide by 1.5. Now that's not bad with these numbers. Sometimes it can be a bit trickier. You should be able to see, like, even if you ignore the decimals, how many 15s are there in 45? Well, that is 3. So I know y is 3. Or you can do it by a trial and error. So you pick a number, let's say 2. Half of 2 is 1. If you add that on, you get 3. So I have to guess somewhere higher. So if you don't like this, you can always do it by trial and error. So that's 3. Half of 3 is 1.5. Add that on, then we have 4.5. Let's have a look at this one. Different shape. They're both mathematically similar. And here I can see they're my two sides that I can work out the scale factor from. So again, it's not doubled, it's not tripled, it's actually 2.5 times bigger. Double it, half it, and then combine those two answers. So I can see here it's times by 2.5. So to go from the smaller one to the bigger one, it's timesing, and there's nothing to say I could have gone from here to here and divided everything. It really doesn't matter. So I'm going to have to times this by 2.5. So like I said, double it, 6, half it, 1.5, combine those two, and that's the easiest way to times by 2.5. So this one must be 7.5, and now we have to go the other way. So I'm going to do it via trial and error. Actually, it's dead easy to divide by 2.5, because how many 2.5s are there in 5? There's 2. And if I guessed 2, doubled is 4, half of that is 1, 4 add 1 is 5, and there you have it. It does get a little bit harder. So when it gets harder, they normally have two shapes, and you should be able to see two triangles here, this one and this one, inside each other. And my advice would be to sketch them separately. So this is 4, so that's 4. This is 12, so I can say this is 12. I know this is x, and you should be able to see a scale factor here of 3. So we know it's 3 times bigger. And the classic error that people do is they divide 10 by 3. And that's wrong, because the 10 is actually this part here, and the x is this part here. I must say now it's not drawn to scale, so the numbers might look a bit odd. So this length here is actually x plus a 10. So we know the scale factor is timesing by 3. So this one times 3 must be equal to that one, following the scale factor. So 3 of those, 3 x's, must be equal to that. Now we've formed an equation which we can solve by subtracting an x to both sides to get 2x is 10, and therefore 1x is 5. And if you put that in, if this is 5, does it follow the scale factor? Times 3, 5 times 3, 15.